All right, welcome to Introduction to Quantum Field Theory. This is episode 26, not 25. 26, and it's on Green's functions. So in field theory, we have, or let's say we have some derivative operator. So we have a derivative operator, partial d. So an example is d equal to, say, the Laplacian, or d equal to the Laplacian plus mass squared. So they're just differential operators of the second order. So if we have this derivative operator, then equations of the form df of x equal to 0, these are homogeneous equations. And a homogeneous equation is an equation that describes a free field. So the free field is this f right here. An example of this is if you would let me click, okay. An example of this is the free field Klein-Gordon equation. So d mu plus m squared c of x mu equals 0. This is a free field equation. So it's a homogeneous equation, and it means a free field. But we also have inhomogeneous equations. We also have inhomogeneous equations. And we'll be saying these a lot, so this. Inhomogeneous equations, where you have the differential operator, you have some general function, and then it's equal to some. All right, so this g and this g are not related. That could be confusing, so I'll write this as h instead. So you can have inhomogeneous equations where the wave, or the thing that represents the wave equation for the field, for example, the Klein-Gordon equation, now is equal to some function. And this function is also a field. So what this describes is some form of interaction, some kind of field interaction. It can be a completely new field, or it can be a self interaction. But in general, this is a inhomogeneous equation, and it describes some form of interaction. The idea we'll discuss is that we can build solutions to these inhomogeneous equations by using special functions, by using special solutions, and we'll label these f of s, which depend on position, but it takes two different forms. So it depends on two positions, such that the derivative operator of these special solutions gives the Dirac delta, which is equal to 1 or 0. And this is if x equals y, x is not equal to y. So if the positions are different, then it's 0. If the positions are the same, then it's 1. So this right here, this f of s, the special solution, this is a Green's function. So a Green's function is some kind of function that when you operate on it with something, you get a Dirac delta. That's kind of the definition of the Green's function. So we will be dealing with these Green functions. We can use these field functions, or these special, what I'll say instead is f of s, x, y, to find the general solution, f of g, which is the solution to the inhomogeneous equation. And generally, this solution, this general solution, is an integral of the field dependent upon y, and then the special solution x and y of x and y, and then integrated over this position y. So this right here is hy. This is field strength, specifically interaction. Interaction field strength. And then this term right here is a sort of damping factor. And what kind of damping? It's basically farther interactions are weaker. So field interactions that are farther away from the source of the interaction or from the main interaction are kind of weaker and they contribute less. So this integral looks at the interaction field strength and then these damping factors and sums them all up and gives you the general solution. To illustrate these ideas a little bit, we will consider the inhomogeneous Klein-Gordon equation, where we have d mu plus m squared operating on the field, which is a general solution and is dependent upon the space-time position. Then we can say that this is equal to a derivative, some derivative here with respect to the field. So this is the form of the inhomogeneous Klein-Gordon equation. So the V here represents some potential energy function, and therefore this is the interaction, the derivative of it with respect to the field is the interaction field strength. So the next step is to suppose suppose that there exists a special field solution dependent upon x mu and some other position, y mu, such that there's something in my throat, excuse me, which is the Klein-Gordon equation, d squared plus m squared, and then the special field solution results in the Dirac equation. Not Dirac equation, sorry, the Dirac delta function. They're two very different concepts. Okay. Therefore, following this procedure where we find the general solution, we can say that, therefore, the general field, x mu, is equal to the integral over four-dimensional space of the derivative, the gradient, here times the s x mu and then y mu, like so. So therefore, a general field solution will look like this. Now, in the next video, we'll be talking more about what the specific forms of this special solution look like. We will see what they look like and how this simplifies the equation. Let me put this on work. So typically, just for some simplification of notation, typically we rewrite this derivative right here as being equal to just v prime, phi of g, or of phi g. So it's easier to rewrite this or the solution to this inhomogeneous equation as the integral over space-time of v prime of phi g times phi s x mu y mu. And this would be typically how it's written. So here you have your interacting field strength. Field strength. And then here you have, so I'm going to write this in the damping factor, but I'm going to write it in slightly different terms. So it tells you how far away interactions contribute to so basically how far away interactions at y mu not equal to x mu contribute to the local interaction. I'll just forget this right here. Contribute to the local interaction. Or what I would rather say, the local interaction, I'd say to the general field solution. So this tells you how strong the interaction field is. This tells you how points far away contribute to the general field solution. So this total field solution is the sum of all of the potential interaction points times the strength of those interaction points, and then the sum of them. So we will be dealing with there's just one last thing before this video ends, which is an identity that we will use lots. So that is the Dirac delta. And it is that the integral over spacetime, not k, y. Oh, no, it is k. Okay. I don't know why I erased that. It's the integral over k, which, if you recall, is the wave vector, or basically represents momentum, 2 pi to the fourth of this minus I k superscript mu, and then x mu minus y mu. This right here is equal to the Dirac delta, x mu minus y mu. And the important thing is right here, we can break this up into two factors, e to the minus I and e to the positive I. And these terms, so the integral over these terms cancels out everywhere except at x mu equals y mu, which therefore acts as a focal point. So you can think about, if you're taking the integral over k here, and you have two positions, then this is position 1, this is position 2, as this varies, then on average, if you have this being different than this, then you could mirror it just by swapping the labels x and y, and they cancel out exactly, or you have two terms, one that'll be opposite to itself, so they will cancel out. Whereas when they are the same, when you swap them, they will always reduce to 1. So this ends up being at 1 at only points where x and y are the same, which is what this Dirac delta is saying. So this is an integral that basically looks over the phase difference between these two waves, and then the phase difference is only 0 at the same points, so you get the Dirac delta.